Hello, everyone. Thank you for joining us here with our session with Ron. I'm just going to give another minute or two, as I think the other session's just wrapping up, and want to make sure that everyone has time to come in. So let's give it a minute or so people can enter the room before we start. Hope everyone enjoyed that session with Caniture. And I think it's all going very well today. And I'm very excited about this next presentation with Ron. So. See people coming into the room. And always, just for everyone's, if you ever want to review these sessions again, please log back into the software. I think it's still live on the site for about 30 days or so on. So you can always come back within the next month, review any of the videos. We will also be placing the videos up on our training site, trainingtrades.ca, and on our YouTube channel. So you can always go there to review them as well. So see, a lot of people have come in, so let's get started. This session is with Ron Blutrich. Ron is the CEO and co-founder of Clear Inc. After a personal experience with a waterborne parasite during his PhD studies, he began researching water quality and treatment technologies. Upon discovering the severe impacts of water quality risks, even in developed urban settings, he founded Clear Inc. with the mission of bringing affordable and effective water quality solutions to every building across all levels of society. With installations at over 15 properties throughout North America, serving over 3,000 families, Clear Inc. is rapidly becoming a leader in UV water treatment. And I just want to say, I got introduced to Ron through Shelley at the CWQA, who heard him speak at another conference, and she said, "You got to get this guy to speak. He's amazing." So I'm excited. I haven't heard him, so I'm excited to hear him. So thank you, Ron, for joining us, and I will turn it over to you. If any of you guys have questions, though, throughout the presentation, you can certainly put them in the chat. We are going to save the questions till the end, and Ron will kind of take care of the questions at the end. But please put them in the chat. I'll keep note of them, and I'll make sure that your questions are answered at the end. So over to you, Ron. Thanks for joining us.
Perfect. Thank you so much, Mark. And thank you for all of the organizers of this and for the invite to give a talk here. I'm actually very, very excited to speak to the Canadian plumbers in the world. And, we're a Toronto-based company headquartered here in Toronto. And I think actually this is a very interesting concept, but the UV industry is actually a very Canadian industry. It's actually a very even Ontario-based industry. Some of the largest UV manufacturers are based out here. So we should actually be very proud of that. My talk today is just about, it's more of a technical session about UV disinfection in premise plumbing. So this is all about trying to maybe introduce or maybe just reinforce some of the information that some of you might have already related to UV. I want to start with just a quick poll, just sort of I want to understand, have any of you ever used a UV system for building plumbing systems in the past? So I think, Mark, if you can activate the polls, then everybody can just go to that poll tab and start to the second poll. So the first poll. Yeah. Perfect. Okay, excellent. Wow. Okay, so it's above 85%, 90%. That's very good. So it looks like a lot of you may have already been familiar with UV, and so I'd be happy to answer any questions you guys have based on this presentation towards the end. So I'll let the poll continue, and we'll start the presentation. So essentially, what UV is managing is microbial contamination. And so the question really comes, where is the source of microbial contamination in our water systems? And really, it starts, at the source, in your lakes, in your groundwater, in your wells. I mean, they're teeming with bacteria, teeming with viruses, parasites, right? But generally, in a city like Toronto, we have a very advanced treatment plant that takes care of a lot of those issues. However, between the treatment plant and the actual consumer, there's a few other steps that microbial contaminations can enter into the picture. The city pipe distribution is a very, very well-known one because those pipes are old, they crack, they leak, And especially when there's a low flow, low pressure situation, sometimes you can have contaminants from outside of the pipe actually enter into the pipe. So this can create a lot of cross contamination, especially with sewage. But then even if it got through the city distribution totally fine, once it enters your building, now in the premise plumbing, it's a whole other type of microbial contamination that can occur. And that's through the formation of biofilms that build up, especially in older buildings, inside the pipes of your building itself. And that will actually harbor a whole ecosystem of bacteria that will continue to grow there and even be resistant to disinfection methods like chlorine. Finally, at the point of use and the showers and in the taps, small aerators and small filters that we have on this side are also very common sources of biofilm-associated bacteria and biology. So generally, these bacterial risks are given quite a lot of focus due to their health risks. And as I mentioned, we have the enteric contamination side, which are things like E. coli, sewage contamination, coliforms. And when you get a boil water advisory, most of the time they're precautionary. There's a low flow, low pressure event, and now there's an assumption that there's going to be a reversal of the pressure, and things from outside will come into the pipe, creating sewage contamination in that sense. The other one is going to be the biofilms that actually form inside of our pipes and become a habitat, something that grows the bacteria inside the pipes themselves. In terms of biofilms, they are supporting rapid growth, and they create these pathogen risks, and some of those pathogens are actually very, very dangerous. But on top of that, the biofilms themselves can create a corrosive effect inside your pipe. So it reduces the longevity of your plumbing systems by having these biofilms present. So generally, the proactive prevention is the best approach to managing biofilm, especially when you finish a new building. How do you keep those clean, fresh pipes clean for long? And this is where we need to come up with better solutions to try to prevent biofilm from accumulating inside of our pipes. Legionella is, maybe some of you have heard of Legionella, but it's actually a very serious health risk that's associated with biofilms. And it doesn't matter if you're in an urban core or in a rural area, it's actually the leading concern when it comes to the health aspect of the microbial contamination in our water. It's when people get Legionnaire's disease, it's like a 25% case fatality rate. So it's understood to be a very, very deadly bacteria and a very deadly disease. And a big part of it is that it creates a pneumonia that ends up being quite deadly. The crazy part about it is that the disease incidence rate has actually risen 9 to 10 times. You see this dip that came during the COVID era, but now it's recovering from that dip. The point is that Legionnaire's disease is getting worse, not just in the US and Canada as well, in Ontario, in Europe. And there's actually a lot of debate about what's actually going on. Why is Legionnaire's increasing so rapidly? Whether or not we know why, we know that it is. And so this is something that's now something we have to deal with. So generally, urban plumbing systems are at a high risk for Legionella, and it grows within the biofilms. So preventing biofilms is also about preventing Legionella. ASHRAE 188 is a whole guideline about how to manage building water systems to manage Legionella. And so when you look at ASHRAE 188, you'll actually find a lot of guidance related to minimum disinfectant residuals, minimum hot water temperature. Actually, that's a very important one. Legionella is most likely going to grow explosively within hot water systems. I visited a lot of buildings now where you'll go and you'll see the hot water system set at a specific temperature that's actually well below the ASHRAE guidelines. So ASHRAE guidelines suggest that we keep our hot water tanks above 60 degrees Celsius. And at least for electric water heaters in Ontario, that's part of building code. But the amount of times that I've seen 50 degrees Celsius, 45 degrees Celsius, yes, it saves energy. Yes, it reduces scalding risks, especially if you don't have any anti-scalding devices, but it creates Legionella risk. And so this is something where I've seen that tension before when I talk to engineers and when I talk to contractors and plumbers. They say, look, I would love to increase the temperature of my hot water system to prevent Legionella, but I don't have any anti-scalding devices right now. And I don't want to basically potentially burn and scald the downstream residents. So this is something where, especially for an existing and older building that doesn't have those protections, sometimes it's just not feasible to increase the temperature, let alone all of the excess energy costs that comes from increasing temperature, let alone also the effect of the increased scaling that occurs at higher temperatures as well. So we want to avoid the hot water temperatures, but that is actually one of the most important ways to manage Legionella. A secondary way is the UV, which I'm about to explain to you. ASHRAE 188 is also talking about building water management plans, which are mandatory for hospitals and lots of healthcare facilities. And these building water management plans, we also are a part of, and we're integrating UV into how those management plans work. So it tells you what to test, how often to test, and then what to do when the tests don't come out favorably. What are the kinds of mitigation steps that you have to take in order to follow that building water management plan? So maybe some of you guys are already familiar with ASHRAE 188, but if not, I mean, it at least shows just how serious it is to manage Legionella in a plumbing system in urban settings. So generally, UV as a method for water disinfection, right? This is something where I've actually seen a lot of confusion about in terms of how do classical filters work to actually prevent bacteria. So when people have worked with reverse osmosis systems or even carbon filters or ultrafine filters, those are physical filters that may have pore sizes small enough to capture different types of bacteria and prevent them from moving forwards and downstream. But you're not really killing the bacteria, right? They're coming onto the filters and they're staying there. And in fact, they grow there. So the truth is that physical barriers may trap bacteria, but they don't actually solve the problem. And if those filters are not maintained, can actually become the source of a problem. And this is something I'm going to show you a little bit later as well. Chlorine injection in general is another solution. So if you've ever been, I went to a hotel in the Bahamas and all they were doing was injecting the whole system with massive amounts of chlorine to manage Legionella risks. I mean, you go in there, you turn the shower, and the whole room smells like chlorine. It's not ideal. It's not good for people's health to overdo the chlorine. It's not good for people's hair, for skin, for even the taste and the smell that comes from the water. Not to mention that high levels of chlorine create what's called disinfection byproducts, which is actually a very serious area of research right now, how to manage the different disinfection byproducts, which a lot of them can actually be carcinogenic. So chlorine itself comes with a lot of issues that, it becomes preferable and even healthier to try to find an alternative solution such as UV. UV, as opposed to chlorine, it's not a residual, but it's a single point of disinfection within your plumbing systems. It's like a barrier or a firewall, you can say. And the way it works is that it's just using a very powerful light that's targeting the parts of the microorganisms that help to sterilize and therefore disinfect the water. It doesn't involve any introductions of any byproducts or chemical additives, and it is essentially the healthiest and most effective form of water disinfection. And it's a very old technology. It's something that's been around for more than 100 years, and it's been applied in many different applications very successfully. UV now, in a technical sense, is somewhere on the electromagnetic spectrum. So it's a type of light, just like visible light. But when you go into the shorter waves past the violet of the rainbow, you start to enter the UVA, UVB, and the UVC. Now, the UVC wavelengths, those are the wavelengths that are doing the disinfection. The UVC is able to target specifically the DNA, the core of those bacteria, of the biology, and it breaks apart that DNA and prevents those bacteria, those microorganisms from reproducing, from infecting, from pretty much doing anything. It completely deactivates those kinds of microorganisms. And it may actually have some other effects as well, depending on what wavelengths of UV you're using. You may also alter some aspects of water chemistry. For instance, some UV systems actually actively dechlorinate and break apart the chlorine inside the water, as well as a few other very, very common molecules. For instance, hydrogen sulfide is something that we've seen a lot in Florida. It has a very big sulfur smell that comes out of the water. It's usually caused by a sulfur bacteria. Now, the UV deals with the bacteria, but on top of it, the UV also directly denatures the hydrogen sulfide. So it has a direct effect at reducing those kinds of molecules. So the point here is that the UV, even though it's targeting bacteria and microbiology, may have other effects on other types of molecules, such as hydrogen sulfide, such as chlorine. and a few others as well. So it does actually a little bit more, and this is something a lot of people don't know. It does a little bit more than just disinfecting the biology in the water. In general, it's very important to understand when you're applying a UV system into anywhere, you must understand three aspects in order to understand what the UV dose is, what kind of disinfection you're providing. Just putting a light in a tube and just hoping that it's doing your disinfection for you is not sufficient. You really want to understand what is the true effective dose of UV that I'm applying in that pipe. And to do that, there's three different factors you need to consider. UV transmittance. Now, anybody can go and get a portable UVT meter that can help you to measure from the water itself how easily UV is able to move through the water. Okay, and this is given sort of as a percentage of the amount of light, the UV light that's able to penetrate through the water to get to the bacteria. The water flow, that's a very obvious one because it depends on how much time the water is actually spending inside the UV column. So as the water is running faster, if you want the same dose, you're going to need to increase the energy from the lamp. You're going to need to do that to account for the increased water flow. And so you'll see that when we install our systems at Clear, we include a flow meter that directly connects back to the ballast of the UV lamp that allows it to adjust the amount of power to the UV based on the differences of flow. Again, higher flow, you have to have a higher lamp intensity to get to the same dose. At lower flow, you can reduce the energy coming from the lamp and still maintain the same dose. So it's all about, at the end of the day, what is the effective dose that you're providing? And then obviously directly from the lamp, how much power from the UV is emanating from the lamp. So if you know how much power is coming from the lamp, and you know how fast the water is running through, and you know how easily the light gets through the water, now you have a way to calculate the UV dose. And just to give you an understanding of the kinds of doses and what they do to different bacteria, let's say E. coli, which is something we'll find in sewage contamination events, log reduction here is like 10 times reduction. So log 1 is a 10 times reduction, log 2 is 100 times, 1,000 times, 10,000 times, 100,000 time reduction. And generally, UV systems are expected to produce at least a log 4 reduction, at least a 10,000 time reduction. So you can see here that I need a dose of what's called millijoules per centimeter squared. I need 5 millijoules per centimeter squared to do a 4 log reduction of E. coli. But if I wanted to do from 10,000 reduction to 100,000 reduction, I'm going to need to actually double the dose from 5 to 10. And as you can see, Legionella as well, that the dose here, basically, if you're providing a 10 millijoule dose, you're able to do a 5 log reduction of both E. coli and of Legionella. Not every bacteria or parasite or virus has the same susceptibility to UV. So some viruses, you're going to need to do a much higher dose to get the same kind of reduction for. And there are tables out there that can help you to see exactly, let's say you're trying to target specific issues, like a specific virus, you're going to want to perhaps look at the kind of dose you're going to need for the reduction of that virus before you plan out your design of the UV system. So there's tables like this available online, and you can also, if you want, Doctor, message me and I'll be able to provide you all of that information as well. But this is a very, very important thing. If you put in a system that's only doing 2 millijoules effectively, then at the end of the day, you're really not making a big difference to the bacteria coming through. So it's very important to size the equipment correctly and to try to understand the UVT that you're applying it to. Again, from well water, the UVT will be much worse. It will be much lower. So you're going to need to account for a higher intensity from the lamp or at least lower flow rates in order to get the same dose. So you need to understand your application. You need to understand what kind of dose you might actually be providing in that application. Generally, you're going to find in the market 3 different types of UV technologies for water disinfection. The first one is called low pressure UV. This is the most common one, and it's actually going to be the most, the cheapest one off the market as a product. The thing with the low pressure UV is that it's very, very targeted to a single wavelength. So it's targeting just the DNA of the bacteria as much as it can. All of its energy goes into that DNA. However, there are a lot of viruses, for instance, that can resist this low pressure because they have very, very stable DNA molecules. So actually the best way to target them is not through the DNA, it's through the proteins. And for that, you need other wavelengths. The medium pressure has a much broader spectrum of UV, so it does the DNA disinfection, but it also has other wavelengths that target other proteins, other aspects of the bacteria, and other molecules. Like I mentioned chlorine, I mentioned hydrogen sulfide. So medium pressure has a bit of a broader a selection of things that it reduces. And actually, one of the most important aspects for medium pressure in especially high-rise application is that, let's say you want to go into the hot water system to deal with Legionella, low pressure UV systems will not work well in hot water. If the water is too cold, the effectiveness of the UV will go down. If the water is too hot, the effectiveness will go down. If you go to medium pressure, technically it's almost temperature independent, meaning that you can use the medium pressure in any temperature water and it will have the same effect, and you won't have to consider how the temperature is affecting the water. These are the classical technologies. The newest technologies that have just started to come out to the market and are going to basically replace all the other technologies, it's the UV LEDs. This is, we had invisible light. We went from fluorescent lamps to LED lamps very, very, very quickly. That's because the LEDs are much more energy efficient, much more powerful, last much longer, have a lot of benefits. It's only been recently for these products to actually hit the market, and it's emerging. And it's a question not of if, but of when UV LEDs will become the only product that you will find for water disinfection. It's going to be hard to find a situation where after the LEDs become cheaper, that you're still going to want to use a low or medium pressure. So this is not yet a fully developed market for the UV LEDs, but keep your eye on it because this is something that is around the corner and will take over the entire UV disinfection space. Generally, it's one of the best aspects of the UV LED is, as opposed to the low and medium pressure lamps, which need to ignite to turn on, the LEDs can basically turn on and off in a blink with no effect to the lamp. So in a low flow situation or a no flow situation, the UV LEDs can instantly shut off, save that energy, and when the water comes back, we'll turn back on instantly, and basically with no effect to the lamp at all. With low and medium pressure, every ignition will reduce the lifetime to the lamp. So that allows the LEDs to be much more effective in the long run. And so especially in residential applications, this is something that's going to last maybe 10 times longer. Generally, what we've seen with filters, and this is something that we make the case of quite often with the testing that we do. Generally, filters are widely used. I think about 77% of American households rely on filters at some level, maybe in the refrigerator, maybe under the sink. But generally, as I mentioned, filters are trapping the bacteria. They're not killing the bacteria. So over time, the filters actually breed the bacteria. They breed the biology, creating biofilms on the filters themselves. If you put a UV system in front of a filter, of a physical filter, you can actually do the job of disinfecting all of that water, removing the microbiology from that water before it lands in the filter. And this will do two things. One, it's actually going to reduce the amount of time that you need. It's actually going to reduce how often that filter is going to get clogged up with biofilm and how often you're going to need to replace it. So by putting a UV system, you actually increase the lifespan of the existing filters you may have there. So when people say, hey, do I want a UV or do I want a filter? I say, hey, if you're only going to choose one, choose the UV. But if you're going to have a filter, you also need the UV. It's going to help to keep the lifespan of that filter to last longer. But more importantly, it's also going to prevent the growth of especially deadly bacteria in our water systems. Eventually, those biofilms will eat through the filter, eat through the membranes, and start to be released in our water. So generally, you'll see that all the filters you've ever worked with, it will have this sentence. It'll say, do not use with water that is microbiologically unsafe. You must have adequate disinfection before the system. You'll find this, every manufacturer understands this, that their filters on their own should not be used in water that has biology in it. But as we mentioned, it doesn't matter if you're in the middle of downtown Toronto, your water is going to come with biology. So doing that step of disinfecting before the filters is something that's not appreciated enough. But based on what we've seen in the field and what we know, it seems to be actually an essential aspect of putting any filtration system together. So this is data that we've collected, for instance, in a high school in Miami. And what we're showing here is we measured iron-related bacteria and Legionella At the point of entry, we found nothing. So basically, that's not coming from the city. It's not a contamination in the pipes from the city. But as you can see here in the unfiltered line, we actually have a little bit of iron-related bacteria, but no Legionella. But then in the same sink, there's the filtered faucet. And when we measured the filter faucet, we saw almost a 5-6 time increase of the iron-related bacteria. And now we're capturing a significant amount of Legionella as well. When we see this, we're saying, look, I compared an unfiltered line to a filtered line that's taking the same water from the building, but the filtered line is the one that's coming with bacteria. Now, I'm asking you, when people buy filters, I mean, are they expecting for their water to be worse? Probably not. And so this is where, when people spend money and then begin to have the confidence that they're allowed to drink through a filtered faucet, you start to see actually that this is a very significant problem. And also, we know that very few people are constantly maintaining their filters on time. So what we're seeing here is that this is clear that the bacteria is actually growing on the filter itself. And without managing that properly by changing the filters soon enough, or by putting a UV system before the filter, we're actually having consumers drink water they think is safer, but may actually be more dangerous. And I think that the two things together is actually a very, very bad situation. Increased confidence, but actually a worse result. Generally, from all the filtered lines that we've tested, 62% have shown significant bacterial load, including things like Legionella, Mycobacterium, Pseudomonas. Those are all very dangerous biofilm-associated bacteria that we've captured through our own testing on the filtered lines. So it shows that this is actually a very significant problem that's probably affecting many, many consumers across North America. What we do at Clear is that we focus at the point of entry. Instead of coming to install UV systems at every single sink, in every single shower, and every single fountain in a building, we wanted to find a very effective barrier to provide to a whole property. So the UV systems that we're providing here are these inline systems. This is an example of a building in downtown Toronto that's servicing 683 condo units. It's a 6-inch inline system with 2 flanges. And this is a retrofit as well. So we installed this in a tight pump room that was very busy, and we had to do a little bit of maneuvering to make it fit, but it's a very flexible installation. So you can do it in retrofits, no problem. And now all of that water coming in from the city is first getting sterilized by this UV system before going into every single unit. And in a sense, basically sterilizing the water to every single shower, every single tap, every single fountain in the property. So this is something that protects the pipes from biofilm. This protects the building from contamination events and boil water advisories. And it protects the filters that people are using from the buildup of bacteria in those filters as well. So it has a very, very strong protective effect on an entire community at once at a single point of installation with a single point of service. It just makes a lot of sense. These systems themselves, if serviced properly, can last 30 years. And based on that, and based on its effect, we believe that they should be just general building infrastructure, these kinds of disinfection devices at point of entry. This is an example of an installation design drawing that we have here, just to show the curious contractors that are around. And what we see here is the flow meter component that we were talking about. So it can change the UV intensity to maintain the same dose, even as the flow is changing through the system. Then it's an inline system flange. This is a horizontal installation, but you just saw in the picture before a vertical installation. So it has that flexibility going horizontal or vertical. There's a few different valves for testing and for cleaning that we install here as well, including an air release valve. And finally, we put in this bypass. So whenever we need to change a lamp, we don't have to interrupt the water to the building. Here's examples, for instance, of providing these solutions and doing tests before the UV and after the UV. And it shows a couple of things. One, it shows the effectiveness of the UV, but the other aspect is it shows that even in urban centers, the amount of bacteria coming into our water can actually be quite a lot. So what we measured here was a general count of culturable bacteria. And this building, it's actually an affordable housing seniors building in Sacramento downtown. This building is right downtown. It's right next to the new arena that they just built. This is the center of the city. This is not in the outskirts. This is not taking well water. And yet, before the UV, we measured coming in greater than 2,200 CFUs, colony-forming units, which is just a general measure of the amount of bacteria, greater than, because it actually saturated the test. It was much more potentially, but our test wasn't sensitive enough to see exactly how much was coming. But that just shows that it was a saturable amount of bacteria. It was an insane amount of bacteria that we've never seen before, such an amount. Then we were able to see the effectiveness of the UV. Immediately after this UV system, this is our 4-inch system, we showed, we only measured 0.01. So that's, you can see the difference between 2,200 to 0.01. That's a greater than 100,000 times reduction. That's the log 5 that I was showing you before. Here's an example in a more of a rural setting outside of Pennsylvania and Verona, outside of Pittsburgh and Verona, where again, the number of bacteria coming in was about 90 CFU. This is something we see more often, is about the 90 CFU range. And afterwards, it was completely non-detect. So the reduction factor here was greater than a 10 times reduction factor in the field from this smaller UV system that we put in a pit. This was more of a garden style. So they had a pit with the master meter coming in from the city, and we actually installed it in that pit so that we didn't have to install different systems in each of the buildings in the garden style. We just had one system in the pit, basically providing that barrier effect to the whole property at once. The more you centralize, the more cost-effective these solutions are. And so you can see the value of being able to reduce the amount of bacteria constantly coming to these residents, to the seniors here or to the families here. Generally, UV it's a reliable, it's a scalable solution. I showed you how there's enteric contamination that comes in through the pipes. I've shown you the biofilm inside the building plumbing itself is a major source of bacteria, especially the dangerous ones. I've shown you how Legionella, as one of the most dangerous ones that we deal with, is a deadly and a growing risk in our premise plumbing systems. I've shown you that there's unmaintained filters that actually increase the microbiological risks. And generally, I'm making the case that the UV disinfection is an essential component of any of your filtration systems. Should save money on servicing those filters in the long run, but more importantly, protecting the health of the people that are using those filters, who are trusting those filters to improve their water quality. And finally, by providing centralized solutions at the point of entry, you are providing a very scalable, cost-effective solution for entire communities all at once. So it makes a lot of sense. It becomes very cost-effective, and it helps to protect not just the people, but the plumbing, the pipes, prevents the corrosion from the biofilms, and overall increases the longevity of a building. So yeah, I mean, that's where we are. Give a very quick rundown, but maybe that leaves a lot of questions, a lot of time for questions for us. But I think before we get into the questions, maybe we should do this final poll. I'm kind of curious to see if, after what I've expressed, if any of you see that kind of value in providing the point of entry system. And,
yeah, so I'd activated the poll a little early, so obviously it's made a mistake first time. So before the presentation, only it looks like 59% had used IV. We're sticking at 100% now, so that's looking pretty good. So I do have a number of questions for you as people are kind of filling out the poll.
yes.
I do have some questions from them, so let's get into those a little bit. What is the maximum dosing capacities for UV LED?
So the UV LEDs at this point are the ones that we use get to about 16 millijoules. So let me go back to sort of the table that I was showing you here. So at 16 millijoules, we're actually getting above the 5-log reduction of E. coli Legionella, which is good. They are attempting to get it to the 40 millijoule range, but that just becomes more expensive. Currently, the LEDs are just a little bit too expensive. The current products are achieving about 16 millijoules for the LEDs.
Good. And Dexter asked, Bruce, I guess was next, do you produce an NSF unit, and will UV LED meet the requirements for reg facilities?
So it depends what kind of an NSF. You have NSF Class B, and then you have NSF Class A. So the Class B, you need above the 16 millijoules. So the LEDs that we have currently, it's actually a Canadian-made product, first actually designed out of the University of British Columbia, patented there, and then produced in British Columbia as well. So this is truly a Canadian technology. It's a UV LED point of entry device for single homes. So in terms of the flow rate, it goes maybe above to 15 gallons per minute. would be the max. And at that, it's going to be able to produce the 16 millijoules, which gives it the NSF Class B certification. But currently, there are no UV LED products for NSF Class A. So depending on your application, I know that there's a few manufacturers pushing for NSF Class A. It's just currently a little bit too costly to achieve that. But every year, the LEDs are getting more powerful. Every year, the LEDs are getting cheaper. Sooner than later, you're going to see a Class A product on the market.
Great. And Dexter asked, does your UV require a pre-filter to ensure that the UV light will not be blocked and reduce its efficiency?
That's a great question. So that's related to the question about UV transmittance. So there's a few things that can reduce the ability for the light to get through the water. One is going to be actually things like sugar. I mean, even sugar in the water will block the UV from moving through it. But heavy sediments, sand, mud, anything that's coming in, heavy sediment that's opaque, will absorb the UV and create these shadows, these sort of what's called sediment shadows. And actually, bacteria love to ride on the other side of this of these sediments, of these particles as they go through. So generally, it's recommended in a situation, let's say you're going directly from well water, you're going directly from lake water, it is recommended first to do a heavy sediment filter to be able, and sometimes we use one of those spin down filters just to be able to remove some of the heavier sediments. But the other aspect of it is even in the design of the UV reactor itself, there's some UV systems that are just sort of like a light in a pipe, and those will be the cheapest, and others will have reflectors inside the pipe. So the systems that we use will be completely full of this reflection chamber. That means that the UV is actually coming in every single direction because it's reflecting off of the reflection surface, and it's coming in every direction. So there really isn't any capability of having that kind of sediment shadow there. But so generally, if you've got heavily sedimented water, definitely putting in a pre-filter for removing heavy sediments is important. But then also, if you're dealing with that kind of situation, try to find a UV system that has that kind of reflection capability, which prevents the kind of sediment shadowing.
And Dexter was just following up that. What size of pre-filter was it? 5 microns? What size of pre-filter should you have?
It's a good question. I mean, it depends again on like the kind of sediments you're actually getting. But yeah, the 5 micron will be good. That actually might be a bit too small, right? And then you'll have to service that a little bit often. So there's a bit of a trade-off. You don't want to do full filtration before the UV in a sense. So I think you can get away with coarser filters. I don't think you need to go down to the 5 micron.
Okay. And Michael had asked, are you saying we should use filters after UV more often? I would think that using filters before UV to remove particulates and extend UV lifespan.
Yeah, so it's a very, very interesting question. So I mentioned how in the filters, especially the RO filters, you're actually going to capture bacteria and the bacteria will grow on the filters. So you have to use a UV before something like an RO membrane in order to prevent the bacteria from landing on the membrane, growing on the membrane, creating problems on the membrane. In terms of actually doing the pre-filtration, you don't need to pre-filter with an RO system, right? You just need to pre-filter out the heavy sediment. So when we've designed full systems, including big carbon media solutions, we've done a very simple spin down sediment filter, then our UV. So the sediment filter helps the UV perform without the sediment in the water. Then the UV is before the big media filters that we provided, and that prevents the bacteria from growing inside those media filters and increases the lifespan of the much more expensive, much bigger medias that we've brought. And actually, the sediment also helps the media filters by preventing the clogging of heavy sediments inside the media filters as well. So that kind of ordering actually makes a lot of sense. Sediment filter, pre-filter, UV, and then your media filters is a really, really good design. Generally, another concept to remember is that carbon medias are removing chlorine. This is something that it's a big problem because a lot of people will put big carbon media filters at the point of entry of single homes or sometimes larger buildings, and then they remove the chlorine throughout the rest of the plumbing. And that means that the bacteria would love to grow. And then they'll have an RO system underneath the sink somewhere. So now there's no chlorine and you have a membrane, tight membrane, catching all the remaining bacteria coming through, and they're growing now on this RO membrane with no chlorine. Without a secondary disinfection, if you're going to remove the primary disinfection, you must consider putting in a secondary disinfection. The UV would be a good solution for that. I can't tell you the amount of times I've seen nothing but a carbon point of entry that has created more problems than it's solving. And then at the end of the day, you have situations where very famous hotel brands now have massive Legionella outbreaks, and all they were trying to do was trying to filter the water for the hotel guests, and they were trying to do something great. They bring in a big Culligan carbon media filter, they put it at the point of entry, and a year later, they're dealing with 2 Legionella deaths and a big lawsuit. So it's extremely important to, yes, the answer to the question is yes. Any type of filter you guys provide, whether it's carbon, whether it's RO, especially when it's both, you should be putting a UV system before.
Okay, great. And Liam asked, what do you recommend for testing these bacteria at point of use, say on a residential service call?
Okay, so that's actually a really good question. Is the microbiological testing? I'll tell you, there's a lot of ways to do testing, and a lot of them are really bad. So you'll find, just like when people try to sell on Amazon the strips, you can use the strip test to test like physical properties of the water. But they have even these kinds of like little papers that you would have to leave in the water for a little bit and put it in a plastic bag. And if it changes color, then it tells you. Those things you get off Amazon are really, really poor, and they're not quantitative, and they don't really give you a good result. Generally, when it comes to microbiology, this shouldn't be done in a lab. There are a few different detection technologies out there that are being developed to allow people to test very easily on site, but it's just not well developed at this point. When we do our testing, we come in, we put in our gloves, we put on our mask, we take out these sampling bottles that have preservatives in them, we collect the water. Depending what we test, we take first draw or we let it flow before we take the sample. And then we actually have to put it in a cooler with the ice and immediately express send it to a lab that's nearby. The lab that we use is EMSL, which is very big in North America. It's the best microbiological testing laboratory. And at that point, you can actually do a variety of different tests, and we build custom protocols with them. The truth is that without that, it's going to be really hard to know exactly how much of what bacteria may be in the water. So the truth is, this is, I think, one of the biggest difficulties when it comes to providing the use case of these kinds of solutions is like, how do you follow up with the testing? When we did our tests, we did very, very high resolution testing protocols that we developed with EMSL, customized solutions to capture that kind of bacteria within that range. So it's actually just not a simple problem to solve. But if you want to have accurate testing, high sensitivity, high resolution testing, the best way is just to send it directly to the lab. The second best way, which would be easier than having to put it into a cooler and pay for the express shipping, which is the expensive part. An easier way will be TapScore. So TapScore has a pretty general microbiological testing kit. It comes as a box. So you can search up TapScore right now and you'll find them. They'll also be able to test many, many different other aspects of water quality. They do have a kit specific to microbiology. They send you a box. It's supposed to be sort of a do-it-yourself, so anybody can sort of do it, including your clients or the property managers directly can do the testing. And then you put the sample right back in the box, put it in the mail. The shipping label's already on there, and it gets sent for an analysis. The type of analysis they do with TapScore is not as good and not as reliable, but it's still a much better solution than anything you can find on Amazon.
Okay, great. Another question, please tell us the water quality requirements for a UV unit to be effective in disinfection.
Yeah, so it really depends on what that UV unit was designed for. And I'll give you the best example. A great manufacturer that we use quite often here in Toronto, actually out in Scarborough, it's called UV Pure. They've been around for about 20 years, and they develop a very special way of using the low pressure lamps that allows it to work in very low UVT conditions. If the UVT is like below 90%, most other UV products will begin to fail to achieve the doses that they were meant for. So usually, like, once you get to 90%, any percent lower is like you need to put so much more UV to account for that reduction in UVT to get to the same dose. However, this UV Pure product, it's called the Halid system, based here in Toronto. They are designed to achieve good doses, NSF class B and NSF class A, at even low as 30% UVT, which is actually unheard of from other products. So it's specifically designed for that, and that's why they use that system for wastewater. So this is really designed for wastewater plants all across Ontario. There's hundreds of these wastewater plants using these UV systems, and it's because those UV systems were designed to manage at low UVT. There's a few other water quality thresholds that you have to consider. Most of the time in these like let's say you're doing drinking water, you're most of the time never really going to hit those. It includes like the amount of iron, or maybe one other consideration is if you're out in rural areas where they do a lot of farming, if you have a lot of nitrates coming in, then the UV can actually form like ammonia. And if the nitrate concentration is really, really, really high and the UV dose is way too high, then it is possible to start to create this like toxic ammonia. But it's a very, very rare situation that you'd have to look for that. And in that case, you should probably just reduce the UV dose or try to pre-filter out that kind of nitrate beforehand. Those would be sort of the biggest considerations. So like sediment coming in would be a consideration. Just directly measuring the UVT is the most important consideration. And then if in special situations, maybe the nitrates.
Okay. In residential settings, what is the average impact of having a UV system? Oh, how much of an impact is having a UV system on your electrical bill?
Very low. Very, very low, especially when you have that flow meter connected, so that it's changing. Like when you're not using your water, it's not going to be on, right? So it's not like it's constantly taking energy out of you. I'll give you an example. The 6-inch system that I showed you here, which is achieving disinfection for 683 condo units. I mean, this is a 3 kilowatt lamp, right? So for such a big building, and then the lamp is not at 100% power all the time. Usually it's actually between 50 and 60% power. And then when the water is not flowing, it's not on. So let's say out of the 3 kilowatts, per day, it's only really on at that level, like 50% of the time. So it's definitely, this is very, very energy efficient solutions. And actually when we do some energy calculations, for instance, when we think about the ASHRAE building water management plans, they tell you to increase the hot water temperature to deal with Legionella. That kind of thermal disinfection is maybe 10 times more energy intensive than putting a UV system to deal with the Legionella. So UV disinfection is a far more energy efficient solution to Legionella than would be thermal disinfection, as an example. So just this is really where you should be concerned about the energy consumption for managing bacteria. It's coming from increasing your boiler temperatures, increasing your hot water tank set points. That's going to be the real killer on the energy budget. And if you replace that with a UV and you didn't have to increase that temperature, now you're actually going to have significant energy savings.
Cool, great. Another question, does your system have an automatic shutoff if water quality drops or in case of lamp failure?
So it is possible to, because we designed that bypass, so it is possible to have automated valves that, if the temperature gets to a certain point, or if you put any other type of sensor, you can actually turn on the bypass valve and basically get the water to bypass the system. Our systems, like the ones from UV Pure, will actually just directly purge the water into a drain if the temperature is too high. But we don't have like a sensor that measures like nitrates, for instance, coming in. Usually we'll just come in ourselves with a little hack probe and measure the nitrates before and after the system, make sure that it's nowhere close to the levels that could be potentially harmful. And then outside of that, I mean, the only other reason to bypass it is if you're in an NSF class situation where you must maintain a certain dose. In those situations, there's actually two things that happens. One, you actually have a flow restrictor to make sure that the flow going through the system is always below the flow you were sized for, right? So that means that no matter what, you will never get too much flow and too little dose. So in an NSF situation, you're always going to be maintaining the flow at a certain amount below a certain amount in order to maintain the dose above a certain amount. In terms of what happens when the UVT starts to drop, we don't have any automated processes for that, but we have sensors that in real time, we actually get remote access to those sensors and to that data. We'll go on our dashboard and we'll see if the UVT starts to decline too much and the water quality is just getting worse. Then we can't achieve the target dose that we set for, and we come in to service the system. Or we'll have to find some other solution to the water that's coming in through it. But the solution there is just to monitor it. It is possible to create automated valves that relay that information, but it's just not a significant problem at this point.
Great. All right, and what process flow would you recommend? 5 micron filter, then UV before pressure tanks, or pressure tanks, then 5 micron filter before UV, based on the growth of bacteria, and why?
Yeah, I mean, look, anywhere there's a tank, there's a risk of growth, right? Stagnant water is one of the largest risks for growth. So I prefer to put the UV system before any tanks. Generally, we do have designs for after pressure tanks when it's required, but I also like it before a pressurized tank as well. Usually the flow of the water can be slower, and then it prevents any of the bacteria from settling inside the tank downstream and growing inside the tanks. So if you're actually considering the kind of bacterial problems in a building, anywhere there's a tank, especially a tank with hot water, like a hot water storage tank, those have to be treated beforehand. Also, tanks will build up sediment at the bottom. This is another good reason to have that 5 micron filter before, because that sediment at the bottom of those tanks will start to harbor bacteria inside that sediment layer as well. It's actually a very significant problem. And then most people are not cleaning the tanks as often as they should be cleaning them. So definitely, I really like that process diagram. It's the 5 micron, it's the UV, and then it's the tank.
Great. Anybody else have any questions? We've got a few minutes left. I think we've gone through them all. You've handled them quite well, Ron. Thanks. Okay. Well, if nothing else is coming in as I'm wrapping up here, I think we can end it there. And you guys maybe got 5 minutes before our next presentation, which is a panel discussion. Actually, it'll be really interesting on the future of water treatment. But Ron, thank you very much for a great presentation. I really appreciate it. I think it was really good. We had a lot of good questions too. So thanks to all the attendees. I'm sure if you have any questions, Ron would be happy if you wanted to reach out to him directly.
Yes, we do. And we're always looking for contractors wherever we go, and we love to work with you guys. We love to learn about your experiences and the kinds of problems you're dealing with. So reach out to me anytime. You can go on our website, which is clear.inc. You can email me at ron@clear.inc. And I'd be happy to field any questions or just any conversation. Thank you so much, Mark, and for the organizers for bringing me on. And it was a great time to present to you guys. So thank you.
Wonderful. Okay, everyone, you got about 7 minutes before the panel starts, so maybe grab a drink or use the washroom, and we'll see you there. Thanks again, Ron. Everyone, we'll see you in the next session. Take care.
Bye, guys.